Greetings and namaskar to each one who came here to watch this video. Topic of today's video is Coulomb gauge. Well, starting with two Maxwell equations which are written in the form of electromagnetic potentials, that are scalar potential, which is denoted by phi, and the vector potential, that is denoted by A. So these are the two equations. Here this A is the vector potential, this phi is the scalar potential, this mu is the permeability, and this epsilon is permittivity of the medium, and this rho represents the volume charge density. Now moving to the Coulomb gauge. So Coulomb gauge restricts the divergence of the A, which is written as del dot A is equals to 0. So this is the Coulomb gauge condition. Now what we are going to do? We are going to use this condition of the Coulomb gauge in these two Maxwell's equations. So applying the Coulomb gauge condition, del dot A is equals to 0 in equation 1 and in equation 2. So here this del dot A, we are going to put this equals to 0, then this term will vanish. Then the leftover term will be this multiplied by del. So we can write this as it is, and over here only del cross mu epsilon curly phi upon curly t as it is, and the right hand side as it is, that is minus mu j. And in the second equation this term will get vanish as del dot A is equals to 0. So these two terms as it is over here, and the leftover part, that is mu epsilon curly square phi upon curly t square when we multiply this by this, which is equals to minus rho upon epsilon. And now here you can see these two terms are same but with opposite sign, that is minus mu epsilon curly square phi upon curly t square plus mu epsilon curly square phi upon curly t square. So we can cancel out these two terms. Now we are left with del square phi is equals to minus rho upon epsilon, and this is a very well known equation which is known as Poisson's equation. Mark these equation as third and fourth. And now it's time to write the solution of the Poisson's equation. So this equation represents the solution of the Poisson's equation, that is phi x alpha comma t is equals to 1 upon 4 pi epsilon integration rho x dash alpha comma t upon r dv dash. So as you can see here, two different coordinates are used as x alpha and x dash alpha. So what are they? So consider that this is the point S, this is the source point, and here we have the another point, that is F. This is the field point, and this distance between S and F is R, and this point S has the coordinates x dash alpha comma t, and this point F, that is field point, has coordinate x alpha comma t. So x alpha comma t are the coordinates of the field point, x alpha dash comma t are the coordinates of the source point, r is the distance between S and F, and this dv dash is the arbitrary volume element at S. Now just writing this equation in more simpler form, we just removed the coordinates and written this equation like this, that is phi is equals to 1 upon 4 pi epsilon integration rho upon r dv dash, and mark it as fifth equation. Now let's take the current density, that is J. J is decomposed into two pieces, that is JL plus JT, means J is written as JL plus JT, where JL is the longitudinal current density and JT is the transverse current density. Now we are going to write the two conditions, one for JL and the other for JT, that is del cross JL is equals to 0 and del dot JT is equals to 0. These are the condition, one for the JL and the other for the JT. Now we are going to take a vector identity for J. Del cross J is equals to del dot J minus del square J. Now simply we are going to carry this term over left hand side and this to the right hand side. So it can be written as del square J is equals to del dot J, this term over here, that is minus del cross J. Now what we are going to do, we are going to place the value of J from the sixth equation, that is J is equals to JL plus JT over here, like del square JL plus JT. We will multiply these two terms by del square, so we will get del square JL plus del square JT is equals to del dot J minus del cross J. Now, comparing the terms of right hand side and left hand side, we get these two equations, 7th and 8th equation, that is del square JL is equals to del dot J and del square JT is equals to minus del cross J. Now, simply we are going to take the solution of these two equations, that is 7th equation and 8th equation. So, these are the two solutions of these equations, and we will mark the solution of JL as the 9th, because we are going to use the solution of JL. So, it is JL is equals to minus 1 upon 4 pi del integration del dot J upon R dv dash. Now, we are going to use the value of the J from the 6th equation in 3rd equation. Here, we will going to put the value of J, and we are going to carry this term over right hand side. Why? Because left hand side will have only vector potential terms. So this is what we get after using the 6th equation and the 3rd. Del square A minus mu epsilon curly square A upon curly T square is equals to mu epsilon del curly phi upon curly T minus mu JL plus JT. Mark it as 10th equation. Now, as you can see, the left hand side has only vector potential, right hand side has one term with the scalar, and the rest one is the current density, that is J. So now it's time to use this first term, and we are going to solve it to make the equations more simpler. Now let's solve the first term from the right hand side. So how we are going to solve it? We have written this term as it is, and we have taken phi separately. And as we know, the value of phi, that is 1 upon 4 pi epsilon integration rho upon R dv. So we are going to use the value of phi over here. Now cancelling the epsilon by epsilon, and we are going to multiply this curly upon curly T with rho. Mu upon 4 pi del integration curly rho upon curly T upon R dv dash. Now if you remember the equation of continuity, it says curly rho upon curly T plus del dot J is equals to 0. So from here we can write curly rho upon curly T is equals to minus del dot J, and we can now use this del dot J over here at the place of curly rho upon curly T. So it is written like this. Now we are going to write this mu separately outside and the rest over term in the square box. And from the 9th equation, that is this equation, that is JL is equals to minus 1 upon 4 pi del integration del dot J upon R dv. So we are going to write JL at the place of this term that we get here in this square box. So finally we get mu epsilon del curly phi upon curly T is equals to mu JL. Mark it as 11th equation. So now it's time to put this 11th equation in the 10th equation. We will get, using 11th and 10th, we get del square A minus mu epsilon curly square A upon curly T square is equals to mu JL minus mu JL minus mu JT. As you can see, these both are the same with opposite sign, so we can cancel them out and we are only left with minus mu JT. And from here we are taking A common outside, and the leftover term in the bracket, that is del square minus mu epsilon curly square upon curly T square. And if you remember from the last video, this has given a particular operator, and that operator is known as the D'Alembert operator, or we can also say the D'Alembertian operator, which is written with the square box. So the final equation that we get is the D'Alembertian operator A is equals to minus mu JT. Here this D'Alembertian operator is equals to del square minus mu epsilon curly square upon curly T square. Well, as I told you, this D'Alembertian operator is 4-dimensional. How? Here you can see del, which has 3 coordinates x, y and z, and there is additional dimension, and that is t. So in all, D'Alembert operator is a four-dimensional operator having x, y, z and t. Well, we are nearly at the end of this video. So this equation in the box, this indicates the source wave equation for the vector potential. As you can see, it has the vector potential and it is expressed in terms of the transverse current density Jt. Therefore, this gauge is also known as transverse gauge. And as you can see from this equation, the Coulomb gauge, only the transverse current, that is Jt, gives rise to the vector potential A, which behaves like a wave. One more name is given to this gauge, and that is radiation gauge. Why? As the transverse radiation fields are given by the vector potential alone. Only vector potential is used. There is no scalar potential. In regions that are far from the electric charge of the scalar potential, the Coulomb gauge becomes zero. So, the Coulomb gauge, that is del dot A is equals to 0, is often used when no source is present. Hence, phi is equals to 0. Now, using the Coulomb gauge, the fields, that is electric field and the magnetic field, is given as E is equals to minus curly A upon curly T and B equals to del cross A. We write electric field E as minus del phi minus curly A upon curly T. As phi is equals to 0, therefore this term will get vanished and the leftover term will be this electric field, that is minus curly A upon curly T. So this is the end of the video. Now let's take a quick review of this derivation again. So this is how we have started with Maxwell's two equations, which are written in terms of electromagnetic potential, that is scalar potential phi and vector potential A. Then we used this Coulomb gauge condition, that is del dot A is equals to 0. We used this condition in the first and the second equation, and then we get these two equations, that is third equation and fourth equation. What we did from here, we have used this Poisson's equation first and we had written the solution of this equation. Then after, we use this J and we use the formula of current density in terms of longitudinal and transverse current density. Then we used its two condition, then one of vector identity for J. Then after solving that vector identity, we went on the solutions of the two equations. After that, we again went on the third equation, and by using the value of J, we rewrite this equation and then we solved it for the scalar potential to make the equation more simpler, and we went on this result, that is equation 11th. Then finally we used that equation 11th in equation 10th and solved it, and here we introduced the D'Alembert operator, and hence we get the final equation in that box, which is the wave equation with vector potential A, which is expressed in terms of the transverse current density, that is Jt. And in last, we introduce another name, that is transverse gauge and then radiation gauge. And finally, using Coulomb gauge condition, we went to know that the scalar potential is 0. Hence, we get these two fields, that is electric field and magnetic field as such. So that's it in today's video. Hope you found this video productive. Thanks for giving your time here. Take care.